In the beginning, by Dr. Walt Brown, we're looking at mysteries. This is part 2, starting here with the Ice Age. Okay. An ice age implies extreme snowfall, which in turn requires cold temperatures and heavy precipitation. Heavy precipitation can occur only if oceans are warm enough to produce heavy evaporation. How could warm oceans exist with cold atmospheric temperatures? Another problem is stopping an ice age once it begins, or beginning an ice age after one ends. As glaciers expand, they reflect more of the sun's radiation away from the Earth and lower temperatures, causing glaciers to grow even more. Eventually, the entire globe should freeze permanently. Conversely, if glaciers shrink, as they have in recent decades, the Earth will reflect less heat into space, warm up, and eventually melt all the glaciers. Don't be misled by claims that there are hundreds of thousands of layers of glacial ice, so the ice age began hundreds or thousands of years ago. Yes, ice cores extracted from deep in glaciers in Antarctica and Greenland have many layers, but the eye can count less than 2,000 annual layers because the weight of the overlying layers compressed all the layers below. They are now so thin that the eye can no longer count them. Those who claim there are hundreds or thousands, or that claim that there are hundreds of thousands of layers, create mathematical models in which some characteristics of the ice core, such as dust content, acidity, or various chemical isotopes, is measured along every millimeter of the core's length. Then mathematical curves having hundreds of thousands of cycles are fit to the data. Missing is the statistical analysis showing that the fit is significant, that the data, such as dust content, acidity, or the variation pattern of oxygen 18, is not random noise. If laymen are not impressed by the claim that it took 800,000 years to lay down all these cycles, those same laymen must be impressed by the technical jargon describing the oxygen 18 or acidity measurements. Hidden is the simple fact that less than 2,000 true annual layers can be counted, even with magnification. Major mountain ranges. How did mountain ranges form and why are they often crumpled like an accordion? See figure 52. Yeah, let's take a look at figure 52. Whoops. Okay, here's figure 52. Buckled mountain textbooks and museums frequently refer to some uplifting force that formed mountains. Can you see an uplifting force by itself would not produce this pattern? Horizontal compression was needed to buckle these sedimentary layers near the Sullivan River in southern British Columbia. Such layers, seen worldwide, must have been soft like wet sand at the time of compression. Today's surface rocks are brittle and cannot bend. Satellite photos of mountain ranges show that some resemble a throw rug pushed against a wall. But what force could push such a long, thick slab of rocks and cause it to buckle and sometimes fold back on itself? Any force pushing on a long, thick slab of rock 8 miles or longer will crush the pushed end before movement could even begin. Therefore, a mountain would not form. See key requirements for folding strata, buckling mountains, and overthrust on page 214. We can see, especially in mountains and road cuts, thinly layered rocks folded like doubled over phone books without stretching the tiny crystalline grains in those folds. Other bent rocks are small enough to hold in one's hand. How could brittle rock, showing little evidence of heating or cracking, fold? Rocks are strong in compression, but weak in tension, so their stretched outer surfaces should have fractured. Bent sedimentary rocks found worldwide often look like compressed and folded layers of wet sand. Obviously, they were squeezed and folded soon after the mushy sediments were laid down, but before they hardened chemically. What squeezed and folded them? Frozen mammoths. Fleshly remains of about 50 elephant-like animals called mammoths and a few rhinoceroses have been found frozen and buried in Siberia and Alaska. One mammoth still had identifiable food in its mouth and digestive tract. To reproduce this result, you would need to suddenly push a well-fed elephant, dead or alive, into a huge freezer whose temperature was 150 degrees below zero Fahrenheit. Anything less severe would result in the animal's internal heat and stomach acids destroying its food. If the animal remained alive for more than a few minutes, one would not expect to find food in its mouth. What could cause such a large, sudden temperature drop? Even if the sun suddenly stopped shining, Earth's temperature would not drop rapidly enough to produce such effects. Finally, you would need to bury your elephant in frozen ground. Quite a trick. How could large herds of elephant-like animals, each requiring much food, live in the Arctic, even if the Arctic were warm? The lack of winter sunlight would allow far less vegetation to grow than is needed to sustain so many large animals. Today, the average January temperature in northern Siberia is negative 28 degrees Fahrenheit. Your nose gets cold after a few minutes in plus 32 degrees Fahrenheit weather. Consider how you would feel if your nose were a 6-foot long trunk and the average temperature was a frigid 60 degrees Fahrenheit colder for weeks. Where would you or a mammoth find drinking water? Overthrusts. For over a century, geologists have struggled unsuccessfully to explain overthrusts. Large blocks of rock, hundreds of feet thick and hundreds of miles long, that have slid horizontally over other rocks for 50 miles or more. Such blocks should have considerable rubble under them. Many have none. Pushing a large slab of rock with enough force to overcome the gigantic friction would crush the slab before it would move. Those who appreciate this problem simply say that poor pressure of water in rocks must have lubricated the sliding as the slab slid downhill. But rocks do not contain nearly enough water to do this, and overthrusted blocks are seldom on steep slopes. Volcanoes and lava. Erupting lava usually exceeds 2,000 degrees Fahrenheit. Where did it come from and why is it so hot? Earth's mantle and inner core are essentially solid. Only the outer core, which lies 1,800 to 3,200 miles below the Earth's surface, is liquid. The standard explanation is that lava, called magma, when it is inside the Earth, originates in hot pockets called magma chambers at depths of about 60 miles. But how did it get there? Then how could a magma escape to the surface? A key fact to remember is that at depths greater than about 5 miles, pressures are so great that all empty channels through which lava might rise should be squeezed shut. Even if a crack could open, the magma must rise through colder rock. Unless this happened quite rapidly, magma would cool, solidify, and plug up the crack. Also, heat diffuses. So what concentrated enough heat to create the hot pockets and melt vast volumes of rock that erupted in the past? On the Columbia Plateau in the northwestern United States, 64,000 square miles of lava with an average depth of 2/3 of a mile spilled out rapidly underwater. On the Deccan Plateau in western India, lava flooded 200,000 square miles to an average depth of 3/4 of a mile. In southwestern Siberia, lava deposits are many times larger. 4 times more magma spilled out on the Ontog Java Plateau on the floor of the Western Pacific than on the Deccan Plateau. How did so much magma form and how did it get out? Two of the world's deepest drill holes are on the Kola Peninsula in northern Russia and in Germany's northeastern Bavaria. They are drilled to depths of 7.6 miles and 5.7 miles, respectively. Deep in the Russian hole, to everyone's surprise, was hot, salty water flowing through crushed granite. Why was the granite crushed? In the German hole, the drill encountered cracks throughout the lower few miles. All cracks contained salt water with salt concentrations about twice that of seawater. Remember, surface waters cannot seep deeper than 5 miles because the weight of the overlying rock squeezes shut even microscopic flow channels. This deep salt water mystifies geologists. Another surprise was the greater than expected increase in the granite's temperature, which increased with increasing depth, so much so that each drilling project terminated early. This raises the question of why the Earth's crust is so hot. The hydroplate theory provides a simple answer. Geothermal heat. Heat inside the Earth is called geothermal heat. The deeper man has gone into the Earth, first in the deep caves and mines and later with drills, the hotter the rock generally gets. What is the origin of geothermal heat? Students are frequently told that the Earth slowly evolved by meteoritic impacts that melted the Earth, so geothermal heat is what remains after billions of years. This popular story has several problems. First, the rate of temperature increases with depth, called the temperature gradient, varies even in rocks far from volcanoes by at least a factor of 6. If the Earth has been cooling for billions of years, one would expect very uniform temperature increases with depth at most locations. Usually hot or cold regions should not exist because the heat diffuses from hotter to colder regions. Mathematical solutions for heat conduction in spheres such as the Earth are well known. These solutions can incorporate many facts, including the Earth's thermal properties, radioactive heat generation, and temperatures at the Earth's surface. Such an analysis are hopelessly inconsistent with the molten Earth story and billions of years of cooling. See Molten Earth on page 36. Oops. Rapid cooling. What then generated geothermal heat, and why does it still vary so widely?